Welcome everybody to this no snow Tuesday, and excited to take a look at expanding our trigonometry knowledge today, building off of the review that we completed yesterday of grade 10 topics. In grade 10, trigonometry is connected to triangles, of course, but we can actually use trigonometry for angles that are above 180 degrees. We don't find angles above 180 degrees inside a triangle unless it's an imaginary triangle that exists in some weird dimension with more angles available to it. And we can use trigonometry on angles greater than 360 degrees. And these are the ideas that we're going to be taking a look at today. When we free trigonometry from triangles and connect it only to angles, we're going to find that this idea of the unit circle and the xy plane is very useful. And we're going to take an arm, it's called the terminal arm, and we're going to rotate that around by some angle. And then we can use the x and the y coordinates of the end point of that line to calculate various trigonometric ratios. So the practice problems for today, we're actually covering 3 topics. The practice problems are in the expectations checklist, which is on the D2L, and they're these ones here, these textbook problems. If I zoom in, you can see it better. There you go. So these are they, and I'll post those after the lesson. So let's take a look. In your handouts, you have angles in standard position, and that's where we'll start. So putting trigonometry onto the coordinate plane, we can draw them using the x-axis as the reference point. X-axis is kind of our 0 degrees angle here. And of course, we label it as follows with the x and the y and things there. Now, in the standard position, we're going to want these definitions for terminal arm and initial arm. So you're going to want to take these down. The standard position of an angle is, and I'll just move this over here so perhaps you can see it in the video. The standard position of an angle, here's our x-axis, and the angle should start with its origin at 0, 0, and it's going to move in this direction as the angle increases. These are increasing angles this way. So here I've shown you a 30-degree angle, and it has this endpoint. The x-coordinate is given by sine of that angle, and the y-coordinate is given by cosine of that angle. We'll get to that in more detail in a second. But that's the standard position of an angle that we're going to be looking at. The terminal arm is that line that we rotate this way. If my elbow is the origin and I start rotating that this way, that's the terminal arm sweeping through the first quadrant, going into the second quadrant, and into the third quadrant there, and then down into the fourth quadrant. The initial arm, that's the arm of the angle that's on the x-axis. If you imagine that here there's an angle arm and then another angle that opens up between those two, this is the initial and this is the terminal arm. This is where the angle ends, that's where it begins. So we have initial, terminal. Here I've shown you also a 135-degree angle that rotates this way, and it's kind of the same as a 45-degree rotation that way. But the initial arm is here, and the terminal arm is there. Initial arm, it's always this positive x-axis here. And so here we see another picture here. This is standard position. This is what we're going to be working with. If you get things that are drawn in non-standard position like this, like here is an initial arm and a terminal arm there, and that's some kind of angle that's been rotated. But that doesn't have the x-axis as an initial arm, so that's not standard. If you see a question that way, you'll often rotate it so that it does correspond to those values. Is that right? Yeah, sure thing. And then this angle is also not in standard position because it doesn't begin at the origin 0, 0. So here is our terminal arm, here's our angle of interest, and there's the initial arm there. The initial arm has a degree value of 0. So let's take a look at the terminal arm for each angle, and I want people to draw angles that have these degrees. So you're going to, if you have several colors, that would be good, and you can highlight in different colors here. What these are going to look like, if I have an angle here that wants to be 60 degrees, then what I'm going to do is start my angle here, and I want to draw it up at 60 degrees there. So what I can do is go up there, I happen to know that this point will be on that angle, and I'll show you why in a second. And then I can just draw that on there, like that. There is an angle that is 60 degrees, and I'll zoom in a little bit because this is too small. There. So that's a 60-degree angle there. If I want a 300-degree angle, well, that's actually going to be rather similar to the 60-degree angle. 360 degrees would be I go all the way around the circle, and then I just need to back off by 60 degrees. If I want 300 degrees, it means go all the way around the circle, but leave 60 degrees. So that's going to be down here. It's going to go to this point, and it's going to go all the way to there. That's a 300-degree angle. It looks like this. It's 300 degrees. Okay. And now we could take a look at 150 degrees. Well, which quadrant is 150 degrees going to end up in? Yeah, it's going to be in the second quadrant. The way we know is if the angle is between 0 and 90, then the angle is going to be in the first quadrant. If it's between 90 and 180, it'll be in the second quadrant. So let's just label our quadrants here. This is number 2, this is number 1, this is number 3, and this is number 4. So that's a 300-degree angle. The 300-degree angle would be the same as doing negative 60 degrees. It's the exact same angle as negative 60 degrees. And yes, we can have negative degrees now that our degrees have a direction, counterclockwise or Widdershins for some reason. Now, let's take a look at 150 degrees. So that would be the same thing as doing an angle that was 30 degrees less than 180. So 30 degrees less than 180, I happen to know that this point and this point are going to be on it. So we're going to go to there, and we're going to go straight in here. So that one there, that's 150 degrees. And then 210 degrees, well, which quadrant is 210 degrees going to fall in? Yeah, in the third quadrant. So 210 degrees is like 30 degrees more than 180. So this one here is like 30 degrees less than 180. This is less 30 degrees. If I do more than 30 degrees, that's basically just a reflection through the y-axis of that angle there. So I'm going to use another color here. We've got red, we'll do purple. Okay. So here, if I reflect this angle through the y-axis, that will give me 210 degrees. Oh, and I'm not drawing. Whee. So that there, 210 degrees. Okay. And so that's what angles in standard position are going to look like. You can think of them, you can visualize them as rotations around the origin. And we go counterclockwise to count positive degrees and clockwise to count negative degrees. Oops. Less. What's that? Oh, sorry, that was in the hallway. Okay. Now, when we're looking at the trigonometric ratios of these different angles, we're going to find that these ratios are all related to ones that we can find in the first quadrant, but the signs of these are going to change. And when we're looking at what was called the cast rule is telling us if an angle lies inside that quadrant, which of the trigonometric ratios are going to be positive and which ones are going to be negative. So if you can remember cast, C-A-S-T, starting from the fourth quadrant for some reason and going counterclockwise, in the first quadrant, all of our trigonometric ratios are positive. So sine and cosine of any angle that's in here will all be between 0 and 1. Tangent will have values that are between 0 and infinity in this area here. And then once we go into the second quadrant, you can also connect this. We're going to be talking about the unit circle in a moment, and I'll just take a moment to talk about the unit circle here. Here, if I take a look at this circle, this point can be thought of as a triangle. And here's the triangle that I can use to think of that point. Here's the hypotenuse, or h, and the hypotenuse is 1 in this case. This side here, this is the y value of the angle. Did I do this wrong? I think I did this wrong. I often flip my stuff. So, yeah, this is wrong. As you know, I often invert my x and my y coordinates. This is one of my common mistakes. Anyway, here's my opposite. This is the opposite side to this angle of interest. And so opposite over hypotenuse would be given by sine. Sine is opposite over hypotenuse. Cosine gives me the x value of this angle. And so cosine here would give me the x value of this point. So through here, we have positive x and positive y values. That's why both of these will be positive for any angle between here and here. But as soon as I go over here, I have negative x values over here. Yes, ma'am. So over here, the x values are negative. That's telling me that my values of cosine over here will be negative. But sine is built out of these y values. Y is still positive over here. So we're going to have positive values of sine in this area. And that's why we see these positive values here for sine, because the y values are positive. And the y is going to correspond. If you just go ahead and sketch an angle over here, it's quite illustrative. Where did I put my stylus? Over here. And my head? Okay, on my shoulders. All right, so over here, if I had an angle, let's say it goes up to here and ends there, we'll notice that this is the point negative 3, 3. And 3 corresponds to this part here. That's the opposite. And so the opposite is positive. That means that the sine is going to be positive. But the adjacent over here, that's a negative value. So we're going to have negative values of cosine over here. And because tangent is opposite over adjacent, one of them is negative, one of them is positive. That's why we have negative values of tangent over there. Now, once we go down here, both the opposite and adjacent are going to be negative. So that means tangent will actually be positive because we'd be dividing a negative by a negative. So in this area, these angles between 180 and 270 degrees, these will have a positive value of tangent, but a negative value of sine and cosine. And then over here, only cosine will be positive. Because over here, if I draw an angle, here the opposite is a negative. That's my opposite. So sine would be negative. Because opposite is negative and adjacent is positive, one of them is negative, one of them is positive. Tangent will also be negative. But we have a positive adjacent, so cosine will still be positive. So another way to remember this one is that every trigonometric ratio will be positive in two quadrants and negative in the other two quadrants. And we can use the cast rule as a simple way to remember those. Or if you remember this logic of that the angle is composed of x values and y values, and in some places the x values are positive, in some places they're negative, and that's going to determine whether cosine is negative or positive, for example. So this is our cast rule. So let's take a look at if we can find the sine of each of these expressions using the cast rule. So if we look at sine 45 degrees, is that going to be positive or negative? Well, how do I solve this type of problem? First of all, what quadrant is that angle going to be in? Yeah, this is in the first quadrant because it's 45 degrees. So that's quadrant number 1. And that's going to be a positive angle. Okay? Because all the trigonometric ratios are positive in the first quadrant. Cosine 223. 223, which quadrant is that going to fall in? Third one, yeah, third one. This is going to be, we're going to, from your point of view, it's going to start in the first quadrant, go to 90, go to 180 through the second quadrant, and then down to 230 in the third quadrant down here. Okay, so that, which trigonometric ratios are positive in the third quadrant? Only one of them. Tangent's the only positive one over there. So that's going to be negative. So this is in the third quadrant, and that's going to be negative because it's cosine, it's not tangent. Tangent 157. What quadrant's that in? Second quadrant. It's between 180 and 90. Good. So that's and it's tangent. Where is tangent positive and where is it negative? Yeah, it's positive in the third one. Yeah, so this is going to be negative here. Tangent's positive here, and it's positive there. Because here, you have positive x, positive y. Here you have negative x, negative y. So negative divided by negative is a positive. So that's why tangent, opposite over adjacent, is positive across from itself. Sine is positive over here, and cosine is positive down here. Okay, so this one is negative, because this happens to be in the second quadrant. Sine 143. First of all, which quadrant is that in? Yeah, 2. Yeah. Unless you're, never mind. Yeah, you're telling me it's in 2. This is number 2. Yeah. Okay. I shouldn't do that. Yes, this is in number 2, and in the second quadrant, is sine positive or negative? It's positive there. CAS. S is the second quadrant, so yes, it's positive. You can also think sine is related to y values. It's related to the opposite from the angle of interest. So it's going to be positive because there we have positive values of y. So that's positive. And then cosine 315. Again, which quadrant is that in number 4? Yeah. So which trigonometric ratios are positive in quadrant number 4? Just cosine. So this is the only trigonometric ratio that would be positive there. The only primary trigonometric ratio. Today we'll look at the inverse trigonometric ratios as well. So another concept that's very useful, and we've introduced it a little bit already, is this idea of related acute angles. And you can go ahead and flip the page. So over here, these angles are really helpful for calculating big trigonometric ratios, or the ratios for big angles. Angles where we can't draw triangles, angles where we might lose our intuitive sense of what that is. We can use related acute angles to relate these. So if I have this angle theta here, and I want to rotate it all that way, this angle beta is going to be the related acute angle here, beta. So this angle might be 30 degrees. If theta is 150 degrees, 150 degrees is the same thing as 180 minus 30. And because this creates a reflection in the x-axis, what we're going to have is the same x and y values for the end of that terminal arm, just the sign on the x value is flipped. So we're going to have the same trigonometric ratios, except the signs will change for some of them. The sign would change for tangent, and the sign would change for cosine for those two. But the absolute value would be the same of those two trigonometric ratios. Okay. Now, some points that I made here, we can call these reference angles, or we can call them related acute angles. I tend to call them reference angles. And it's worthwhile to draw some triangles here on your diagram and see that if I have this angle here, here's my related triangle. Remember, these are right angle triangles. So this is the opposite, this is the adjacent, and over here I would have the exact same triangle just flipped over through the x-axis. And this would be the adjacent, and this would be the opposite. The relationship here is that opposite equals opposite, but adjacent, they're just negative versions of one another. This is, if this was 3, this would be negative 3. If the opposite was 2, then that would also be 2. And because our trigonometric ratios are, and this is hypotenuse, and the hypotenuse is the same in both cases, hypotenuse just measures the length of that arm, so it's always positive. With the unit circle, it's a length of 1. And that's why we get exactly the trigonometry outputs for our x and our y coordinates along that unit circle. So useful to think about these triangles, visualize these triangles, and these ideas will become intuitive. If you don't have a picture in your mind of why these things are the way they are, then this whole lesson, this whole topic becomes a set of definitions that you have to memorize. I know my brain doesn't like working that way. If you're good at memorizing lists of facts and making flashcards and practicing those for your quiz, that would be fine. But I would prefer to think about these as x and y values that make my trigonometric ratios. And just to review here, for angle theta, sine would be opposite over hypotenuse. And the opposite would be the same as this opposite over here. So the sine beta is equal to sine theta. This is sine theta. And then cosine theta would be adjacent over hypotenuse. And that would be the same as the negative value of cosine beta. So cosine beta would be equal to its adjacent over hypotenuse, but that would be equal to the negative cosine of theta, because here we have a negative a value. And then tangent, opposite over adjacent. We see that tangent would be the same as well, except it would be the negative version. So that's the value of seeing these related acute angles. When we rotate into the third quadrant, the related acute angle is how much past the y-axis we go. So it's like a rotation of this angle around the origin, but it's better to think about it as being reflected this way and then reflected that way. You'll notice that beta here, if we reflect that through the x-axis, it would give us the same opposite and adjacent, but both of them would be negative. So this would be the negative opposite, and this would be negative adjacent still. Negative value here, negative value here. And then if we rotate into the fourth quadrant, it's the amount of angle that we didn't go through. So here, beta, if I reflect that through the x-axis, it would give me this one here. So if we're looking at, say, which angles have a reference angle of 20 degrees, we're going to find one of these angles in each one of the quadrants. So in our first quadrant, that would just be 20 degrees is our angle that has a reference angle of 20 degrees. But over here, 180 less 20 degrees, or 160, has the same reference angle as 20 degrees. And that's useful if you want to calculate the sine of 160. You could also calculate the sine of 20 degrees, and it's the same thing. Here, 200 degrees would have a negative sine and a negative cosine of 20 degrees, but the same value tangent. And then 340 degrees, or 360 less 20, that would also have a reference angle of 20 degrees. It would have a positive cosine, but a negative tangent, negative sine. So let's find the related acute angles for these three angles. We may need to draw some diagrams. Yeah. So let's go for it. If we're looking at 135 degrees, what would be the related acute angle? Draw a diagram. We know 135 degrees is going to be over here. Okay. That's 135 degrees. And what's this angle here? That's where we're going to find the related acute angle. Well, it's going to be 180 less this 135. So what's that? This angle here is the related acute angle. We'll call it beta. 45. Yeah. How did you do that? Yeah. Yeah, 180 minus 135. Yeah, that's how you do it. So this is 45 degrees. So now that we've been given a method, how would you calculate the related acute angle for 330? Which quadrant will it be in? In the fourth. So I'm going to go around to 330 degrees. It's going to look something like that. The related acute angle is here. It's always between the terminal arm and the x-axis. What's that angle in there? 30. Good. So this one is 30 degrees. And you can do that by 360 minus 30. Good. 240 degrees. What's the related acute angle? For 240, think about which quadrant it's in. It's in the third. So it's going to go around here to 240. So here we actually want this angle between the x-axis and the terminal arm. So what's that angle going to be? 60. Yeah, 60. So that's a useful idea because this angle 60 degrees, we know its sine, we know its cosine. We're actually going to learn the exact values for those today in a future bit of practice. And yeah, those are related to this angle 240. So now, if we're given a related acute angle and we're told to put that in a certain quadrant, we can actually find that new angle. Again, visualize or draw diagrams to help you get these correct. Here, 70 degrees and the angle is in quadrant 3. So the way I do these ones is I go to quadrant 3 and then I go 70 more degrees. 70 degrees. And I want to know, well, what is that angle if I would have started there? Very good. And you did that by adding 70 plus 180. Yeah. Equals 250 degrees. Good. 54 degrees, but it's in quadrant 4. We measure our terminal angles from here. That's 54. And so we want, here we used addition because we did 180 plus this angle. Here it's much easier to do 360 minus this angle. So what is it? .306. 306. This is angle 306. So this here, if we had to start it at the x-axis, go all the way around with our terminal arm, that gets us to 306. 31 degrees, but it's in quadrant 2. So how will I do this one? Here we go backwards 31 degrees, 31 degrees. So what will I do to find this angle here? Yeah, so what's that?
$149.
Yep, good. So this is 149 degrees. And then 12 degrees, but it's in quadrant 1. What angle is that?
I wonder.
I'll come back to you on that one. Okay, this one is, this we do 0 degrees plus 12, which after you've done, you can do this in as many steps as you like, but that's 12. It's 12 degrees. Okay, it's in quadrant 1, so the reference angle is the angle. That's 12 degrees. It's a trick question. Watch out for these trick questions. Just look at them and say, oh, that's how the teacher could trick us. I'm not trying to trick you, but okay. So if we're given a coordinate point on the terminal arm, this is where, okay, we're finally out of definition area and we're back to doing some math. Okay, well, we were just doing some math, addition, subtraction to find these angles. But now we're going to actually have to do some stuff to find the angle that's made by a point. So the first thing that we would want to do, if we have a problem like this, did this flop onto the next one? Yeah, it did, eh? Okay, so I said solve it. We're going to look at all of this stuff. Okay, we're actually going to come back to that one because we're splitting up the lesson. So first step, plot your point. -6. 1, 2, 3, 4, 5, 6. That's -6. 6, and then 5. 1, 2, 3, 4, 5. Okay? So if I have an angle that's created, and here's the point, negative 6, 5, okay, is created by this, and I want to know what's this angle. Not only do I want to know what is this angle, but I want to know all of the trigonometric ratios associated with this angle here. Call it theta. Theta is a Greek letter. It's the most commonly used variable for an unknown angle. We can use x, but we're often going to be, if we're in the xy plane, we're not going to use x to describe an angle. If you're describing a triangle, sure, no problem. Even with triangles, though, we're often going to use big A, big B, big C, and the corresponding little a, little c, little b to talk about the sides and angles and the related sides, related angles. Generally, with unknown angles, we can call them theta. That's just so common. We're going to use Greek letters. Beta is another common one. Funky B with a little tail on it. And you're going to see a lot of these Greek letters. So we want to find angle theta. So how are we going to do that? Well, the first thing that you're going to do is plot the point, connect the origin to the point. So we did that. And then you're going to create a right triangle by connecting the point to the x-axis. We can solve for the related acute angle using tangent. Okay, so we can find the tangent of this if we create another triangle here. So I'm going to do this next step in another color. And I'm going to create a right angle triangle here. It comes down and goes across. And I know that this has a height of 5 and like an opposite of 5 and an adjacent of 6. And I'm going to be solving for this related acute angle beta. These are by definition going to be acute angles because they're less than 90 degrees. That's why they're so beautiful. And here, so let's find beta. So I know that tan beta is equal to, what's tan beta equal to? Yeah.
Is it 5 over 6?
It is 5 over 6. So the way I solve something like this for beta is I say that beta is equal to the inverse tan of 5 over 6. So that's something that you punch on your calculator. So now I'm going to hear the sound of click, clack, click, clack as everyone calculates this on their calculator and then starts shouting the answer at me. If you get a different answer than your friends, then you need to change the settings of your calculator to get them in degrees and to get it to output decimals for you. If it gives you exact answers, that's a little surprising.
Basically 40 degrees.
Basically 40 degrees? Okay, cool. Other people are getting that, right? Try it on your calculator. Make sure that you know how to punch tan inverse of 5 over 6 to find 39.8, to find that beta is, 39.8 is 40 degrees. Yeah. Cool. So now that we know 40 degrees, we can find theta. So what's theta? Sorry? The big angle, yeah. And then use the appropriate related to acute angle formula to solve the angle in standard position. So here we create our formula by saying 180 minus beta gives us theta. So theta is, still waiting for it. Yeah, 140. Yeah, 180 minus 40, 140. So theta equals 180 minus beta. Theta equals 140. Okay. Now, our angle theta, what's the value of sine for that angle? How would we find that? If you wanted to give me an exact value for its sine. Here we're missing one thing, the hypotenuse. What's the length of the hypotenuse here?
A squared plus b squared.
Is the square of the hypotenuse. Very good.
The square root of a squared plus b squared.
Yeah. So if I want to find the hypotenuse here for this angle, what I can do, and this way I can find things like an exact value for sine theta. Okay? And that's going to be here, negative 6, 5. So what I want to know is what's the hypotenuse. And the hypotenuse squared is going to be equal to the x squared plus the y squared. And that's going to be here, 5 squared is my y squared, so that's 25. X squared is negative 6 squared, so that's positive 36.
Is there supposed to be a place for writing this?
Where you're going to be looking at sine, cosine, all that. Yeah, you can find a spot in there somewhere. And then here, h would then be 36 plus 25 gives me 61. So h would be the square root of 61. So sine theta, I'm going to have that be over 61. That's my so is SOH. Sine is opposite over hypotenuse. So the sine will be something over 61. And what is it? 5 here. 5 is my opposite. Cosine, now that we know that the hypotenuse is root 61, what will the cosine be?
6 over root 61.
What flavor of 6, Siraj?
-6.
Negative 6. So it's as simple as look at the value of the x here. The value of the adjacent is -6. Or you can remember, well, it's going to have the same cosine as beta, except it's going to be negative because cosine is negative in the second quadrant. So we can look at that in a couple ways. And then tangent, we already did, right? Tangent of theta was just opposite over adjacent. So we have 5 over 6. 5 over -6, sorry. And this gives us tangent of theta. Okay. All right. So that's that idea. Now let's go take a look at coterminal angles. This is a very simple idea, and I think you'll have a good intuitive understanding of it if you've already started visualizing these angles. When you have an angle that's greater than 360 degrees, or an angle that's negative, those angles can be the same as other angles because we're going to repeat angles every time we go around 360 degrees. It's just the same. And when we look at the functions for sine and cosine, you're going to see these repetitions as wave-like repetitions, periodically repeating along the x-axis. If we do 840 degrees, that means we've gone around once, twice, and then we finish over here. So 840 degrees, what would that angle be the same as 840 degrees?
140.
120 degrees.
Yeah, 120. And how'd you do that, Suraj?
Basically, 360 is a full circle, right?
Yep.
And there are 2 full circles that could fit in. So you do 360 plus 360, you get 720. Then you do 840 minus 720, and you get 120.
We've got a number of skateboarders and skateboarders, but also snowboarders and skiers. And you're thinking about your 720 and things like that, right? Like different maneuvers that you could do coming out of the half pipe. Well, 720 is just 2 turns. And so if you see here, an 840 would be 2 turns and then a little bit more. How much more? Siraj has told us that's 120 plus 720 is 840. So an angle 840 will have the same trigonometric ratios as the angle 120 because it's the same angle. It's just gone around a few more times. And then negative 240, well, that's the same thing as positive 120 because, hey, if we add this to 360, like we go the other way, then it would be 120. Same thing. So those are just an idea to be aware of. Yeah. So if we had this question here and we want to find angles that are the same as 30 degrees, how could we do that? Give me 3 more angles that have the same values of sine, cosine, tangent as 30 degrees. Liam. Oh, that was just a very, looked like an idea of stretch. Yeah. Okay. I'll do one. Here's my visualization. I imagine going around and stopping at about 30 degrees. So that looks to me like 360 plus 30, that'd be 390 degrees. I just did the easiest one. Someone do some more. That would be the same. Suraj.
330.
330 would have the same value of cosine, but different sine and tangent.
Oh, okay. So it has to be the same terminal arm.
Yeah, same terminal arm.
Okay.
So if you went the other way,
750 then.
750. Okay, yeah. So 390 plus another 360 gives you 750. That's super duper. And we could also go the opposite direction. We could also go this way. So you were almost there. You just had the wrong flavor of 330. Negative 330 would also give us that angle. These are all angles that are the same thing as 30 degrees. Well, they're a little different. In different contexts, you might need to distinguish between these different angles, but they have the same trigonometric ratios. They have the same terminal arm. And we could keep on adding 360s and keep on going around and circle, circle, circle until we end at that point. That's where you'll see, like, find the sine of 2,057,000. Well, you just take out all the 360s that you can and whatever you're left with. So we could also do 36,000,30. That would be the same thing as 30 degrees. Why? Because this is my factor 360. I did 10,000 of those, and then I added another 30 degrees. Another one. All right. So that is this topic. So let's take a look at page 238 in your textbooks, question 1 to 5. And we're going to come back to some of these examples after the break as well. Any questions before I release you to work on these? Yes.